This presentation is delivered by the Stanford Center for Professional Development.
Okay, so we'll start in on finishing up unconstrained optimization. So actually, let me, I want to summarize the, the material we covered last time. So actually, let me do that right now before we jump into the actual lecture. So the summary is something like this. Here's just at the highest level what we did last time. We looked at the gradient method, which is kind of the most obvious thing you would do. You know, you say, which way should I go? Someone says, that's the fastest way downhill. I'll go that direction. I'll adjust my step length. Nothing could be more obvious. The first sort of non-obvious fact about optimization is this. While the gradient method actually can work quite well, if you're lucky, right? If your problem is sort of more or less round, it's not too skewed, you know, the sub-level sets don't look like, you know, cigars or anything like that. In that case, it works, it does and can work very well. So you will see people, you may encounter problems like this yourselves where the gradient method works. For extremely large problems, that's good news because it's just so simple to do. So that can happen. However, the part that's not obvious is this, is that generally speaking, those methods, the gradient methods, don't do very well at all. And in particular, if you give me a problem where it's working well, all I have to do is scale things and I will slow it to, for all practical purposes, a stop. So that's the summary of the gradient method. The other important thing to know about the gradient method is it depends on the coordinates chosen. So if you change coordinates, like just scale the variables, the gradient method, you don't get a commutative diagram. The gradient method changes. And in particular, by change of coordinates, you can make the gradient method get much faster, or you can make it get much slower, or basically slow to, for all practical purposes, a stop. Of course, the theory says it's going to converge, but that's maybe not relevant. Okay? So that's the thing to know about the gradient method. Newton's method is the next one we looked at. Now, Newton's method is affine invariant. So if you change coordinates by an affine transformation, you get a commutative diagram. Newton's method works perfectly. Okay? So you get a perfect commutative diagram. In other words, if you change coordinates, you get the iterates are the changed coordinates versions of the iterates. It works both ways. What this means is that, for example, it's completely unaffected by scaling. It is affected by scaling, but only at the level of numeric. So really quite horrendous and violent scalings are required to make any difference at all. Of course, in infinite precision, it makes no difference at all in Newton's method. Newton's method works very well. It has the other part of the summary is that Newton's method actually, if you look back at the history of optimization, there's even a holdover. A lot of Newton's method was terribly feared, for example, in the 60s. And the things that scared people were, for example, solving a set of linear equations, which you must do at each step of a Newton's method. Okay? N cubed sounded really bad then, and especially, you know, even when n was 100. So again, you have to close your eyes and imagine 1965 or something like that. You also have to remember that a lot of the people teaching you optimization sort of that was when they had their intellectual adolescence. So they were marked and affected by this. So they still will have an aversion to Newton's method. They'll have an aversion to Newton's method because when they were taught optimization, solving 100 linear equations was a big deal. And therefore they were subjected to weeks and weeks and months and books full of things, all of which were about how to avoid Newton's method. Okay, so times have changed, and we can solve sets of 100 equations. How fast? Just roughly. What are how long does it take to solve for a Newton step with 100 variables? Come on. 1,000? Didn't we cover this last week? Aren't you doing it? What? Thank you. Thank you. Okay. Yeah, actually milliseconds, but there's only one character in your statement I don't like. The S at the end. Yeah. So it's typically under actually a millisecond. It's measured in microseconds. Okay? No, just look. It's 1,000 equations takes a second or something like that. And so therefore, do your n cubed, scale it down, you're talking microsecond, talking a millisecond or so. Okay? So the point is, this is not a big deal. Now, that's not to mention the following. In many practical problems, the linear equations you have to solve have structure, like we talked about last week. It's banded, it's block diagonal, it's arrow. All these things are going to come up in many application problems. So signal processing, communications, finance, this structure will come up. That just makes it even faster to solve these things. So I guess my summary is now, past, maybe in the 1960s, it was very important to do everything you could to avoid Newton's method. It's not such a big deal now, especially if you know how to solve linear equations efficiently. So that's the summary of Newton's method. Works really well. I mention this only because you will bump into people who will be trained classically, and they will tell you that in fact 2/3 of a course is devoted essentially to attempting to get out of using Newton's method. So you don't have to be afraid of it. So that's the summary of that. Okay. So last time we looked at the classical convergence analysis, and this is a lead-in to our next topic. So the classical convergence analysis for Newton's method basically says this. It says, we looked at it. The critical thing is a bound on the third derivative. Okay. Now, we discussed that last time. It's totally obvious that the third derivative is what affects Newton's method. Because if the third derivative is 0, the function is quadratic. And Newton's method nails the answer in one step. If L is small, if the third derivative is very small, it means that basically a quadratic model at one place, calculated at one place, is actually a pretty good quadratic model calculated at another. And that's exactly when Newton's method is going to work well. Because it means that when you calculate a quadratic model, it's going to have a huge range of where it predicts well what the function is. That's when Newton's method is going to work well. So everyone agrees the key to Newton's method working well is the third derivative being small. That's obvious. Okay? Now, the classical analysis does that by limiting the derivative. This gets us to actually a very actually the second shortcoming of the classical analysis, or there's a shortcoming of this classical analysis. And let me say what it is. Let me put it in these terms. Let's see, how shall I explain this? Okay, I'll do it this way. You have something like Newton's method, and you have sort of the beautiful math on one side, right? And then you look, and you have like C source on the other. Okay? So that's kind of everything we do looks like that. You have the beautiful theory, and then you have C source. Okay? And what you want, the way the world should be is this. The theory should be beautiful. Like the theory of Newton's method is beautiful. It says basically if you change coordinates, it has no effect on Newton's method. None. Now, when you look in the code or something like that, or I guess you also have the analysis. If you look in the analysis or the code, you actually start seeing things like, so you look in the code and you'd see ugly things like you'd look at a stopping criterion, it'd be the norm is less than some, capital EPS. And you'd have to look at some hash-defined EPS somewhere to find it. And it'd be some number like 1e minus 9. And then you'd challenge the person and say, well, what's that? And the correct response to that is you're not supposed to be looking that closely at my C source. That's the first comment. But the second is something like, well, we tried 1e minus 10, and sometimes we had problems, and 1e minus 5 wasn't a high enough accuracy. So this is the way everyone expects the world to be like this, right? Where there's some things in the C source that are not exactly totally defensible. But anyway, all right. So here's the mathematical analysis. Now let's look at this. The question is we look at the analysis involves norms, but norms change when you change coordinates. So we have a big problem here. The problem is this: an implementation of Newton's method actually is more elegant than the mathematical analysis, because the implementation is, in fact, at least a first order, affine invariant. It doesn't depend on coordinates. But the analysis depends on the norm. So for example, here, if I change coordinates, we know Newton's method doesn't change at all. You generate the same number of iterates. If I rescale x or anything like that, if it took 12 steps before, it takes 12 steps now. But now we go over here and change coordinates. If you change coordinates, everything over here changes. The Lipschitz constant changes, little m changes. The complete analysis. Then so you ask the person the code works perfectly. It takes 12 steps. Change coordinates, it takes 12 steps. Then you ask the person who did the mathematical analysis, in this case Kantorovich, you ask them, what's your upper bound on the number of steps it took? You change coordinates, they say, well, first of all, they say something like it's 5,230 or something like that. That's assuming you even know these numbers, which you don't. Okay? But that's the nature of a bound, right? It's typically useless in practice, right? Then you change coordinates, and they say, oh, now my upper bound is 67,248 iterations. And you say, well, wait a minute. The method itself, the code executes the same if I change coordinates. Why should your bound change? So this is sort of the world is not in balance here, because you have the mathematical analysis is less sophisticated than the code. And it shouldn't be that way. It should be the other way around. It should be the person who wrote the code who has to defend little bits and pieces and things like that, little stuff like that. So that's just wrong. So what this motivates, if for aesthetic, if no other reasons, it motivates the following. We have to have a way to say the third derivative is small that's affine invariant. Because then your mathematical analysis will actually be as aesthetically pleasing and sophisticated as the method itself. Yeah.
What are constants L and M?
That's a Lipschitz, well, no, L is defined right here. That's the Lipschitz constant on the second derivative. M is the strong curvature constant. It's the minimum on the Hessian. Okay? So what we need is a way to say the third derivative is small that's affine invariant. Now, actually, armed only with that hint, you could come up with several methods. One of them is going to be this method called self-concordant. Because when you first see it, it's going to look very sick. You'd look at it and you'd say, who possibly could think of something like that? But with what I just gave you, well, let's see. How could you say, let's just take a scalar, a function on R. How would you say f prime prime is small? Well, you could say this. That's less than L. That's this, okay? That's no good, because I can change coordinates here. And I can make the third derivative, in fact, anything I want. So I can't just do this. So you're tempted to do something like that. That doesn't work because they scale. One scales like the cube, and one scales like the square when you scale the argument. So that hints, actually, that if you want to put these two on the same scale, you're going to have to put like a 3/2 power in there. That's the only way to have a way to say the third derivative is small, but which is a way that's invariant under changes of coordinates. Right? Okay, so that's your hint. Just save that up because it's coming up. Okay, so this leads us to this idea of self-concordance. Not quite sure where the word came from. It was coined by the originators of this. This is from Nesterov and Nemirovsky. I guess it means something like this. Well, we'll see what it means. Actually, it's the Lipschitz constant of the Hessian measured in the coordinate system induced by the Hessian, which sounds weird, but it's not really. So here's what it is. It's going to turn out you're going to get a convergence analysis. So this is one of those cases, which is actually kind of why I don't know. This is kind of a lot of people feel this that if you go after just aesthetics, then often very important practical things will follow. That appears to have often been the case, right? So you have, for lots of stuff in physics and engineering as well. Actually, it works. It's obvious why it would work. Anyway, all right. So if we go after this idea of redoing the classical analysis, but now not using numbers that depend on the coordinate system chosen. So you want to say minimum curvature, you want to say Lipschitz constant, third derivative, you have to bound it in a way that does not depend on the coordinate system. So here's what's going to happen. Turns out this idea of self-concordance, which we'll get to soon, it's absolutely amazing. It turns out it doesn't depend on any unknown constants. So in fact, all the constants will go away. A function is either self-concordant or not, period. It just goes away. There is no constant, and certainly no unknown constant. You get a bound on the number of steps in Newton's method that's affine invariant. So finally now, sort of the mathematical analysis is as sophisticated as the actual method. Okay, so now you have something where when you change coordinates and you ask the person producing the bound whether or not what their new estimate for the number of steps is, they give the same answer as before. And this is actually the key to getting to establishing that, for example, the interior point methods we'll look at next week have polynomial time complexity. So that's the general method. It turns out also that the self-concordance, it's not quite clear what role in practice it has. Well, I'll say more about that later, although it clearly has some, that's for sure. So, okay. So what is self-concordance? Well, here it is. You say that a function from R to R is self-concordant if the third derivative is less than, the 2 is there for a convenience and can be replaced by any constant you like. It doesn't make any difference. So it says the third derivative is less than 2 times the second derivative to the 3/2 power. Now, when you first see this, you think, well, who on earth would come up with this as a way to say the third derivative is small? It just makes no sense. But actually, after a while, if I told you you have to say the third derivative is small, and you have to do it in a method that's affine invariant, that doesn't change when you change coordinates, this is actually one of the only ways you could do it. Now this is much more natural. Right? So they have to, because they just scale differently. Okay, so that's what it means to be self-concordant. All right. Then you say that a function on Rn is self-concordant if it's self-concordant when it's restricted to any line. So that's what this means. Okay, so let's look at some examples. Well, let's see, linear and quadratic, that's easy because the third derivative, everyone agrees linear and quadratic functions actually are very well suited to Newton's method. Actually, linear less so because Newton's method fails instantly. But quadratic, everyone agrees that's perfect because the third derivative is 0. Negative logarithm turns out to satisfy this. So if you just work out, I mean, well, it's not exactly hard to do. You take the third derivative and whatever, and I think actually it's right on the boundary or something like that. You get maybe an equality or something close to equality here. Anyway, whatever it is, it's extremely simple to verify. So the negative logarithm is self-concordant. Turns out there's lots and lots of examples. One example would be something like entropy. Sorry, not entropy. Entropy alone is not self-concordant, but if you add an extra log term, it is. Okay, so that's okay. Now you have affine invariance. This is the whole point. If you change coordinates, in the scalar case, you just scale and shift. The shift doesn't make any difference, but the scale by a does the following. The third derivative scales by a cubed. The second derivative scales like a squared. The 3/2 here and the 3/2 power here basically makes the a drop away. So if f is self-concordant, so is f of ay plus b. Okay? So now you have a self-concordant calculus. And so here are some basic properties. One is it's preserved by scaling, but only if the scaling number is bigger than 1. So scaling a function by a constant bigger than 1 gives you preserves self-concordance. So does sum. It's preserved under affine composition. And then there's a bunch of other stuff. We're not going to go into it too deeply, but for example, there would be a generic result says that if the third derivative is less than 3 times the second derivative divided by x, then this function here is going to be self-concordant. So we're not going to go into details. There's more on it in the book and so on. Okay, but let's look at some examples. The shocking part is that many functions that come up that you will encounter are self-concordant. So that's just, by the way, not all. Good example, entropy. So entropy is not, 1 over x is not, I mean, for example, and all sorts of other things. So, but some are. Here are some examples. Log barrier is self-concordant. Log determinant of a positive definite matrix. By the way, these are just not obvious things like remotely to show. First of all, you don't even want to think about the third derivative of this function. I don't recommend it. I'll tell you why. The third derivative of log det capital I, you barely want to think about the gradient. The gradient is a linear function on symmetric matrices. That's okay, because that has the form of another matrix with in an inner product. The second derivative is a pain. I don't recommend thinking about it. The second derivative of this function here, right, is a bilinear form on symmetric matrices. It has 4 arguments. So unless you're used to dealing with tensors and things like that and can handle them safely, I guess if you come from mechanics or physics or something like that, I don't recommend it. Third derivative, make me laugh. The third derivative here has 6 indices. Everyone agree? So, I mean, unless you're specially trained and certified to think about things with 6 indices, I recommend not doing it. So that's my recommendation. So nevertheless, I'm talking about just thinking about what the third derivative is. Nevertheless, the third derivative of this is less than twice times the second derivative to the 3/2 power. And it's actually using the calculus here. You can show this. Other examples. This is the so-called barrier for the second order cone. So there's plenty. We'll get to that. Okay, so why do you care about self-concordance calculus? Actually, I'll come back to that question several times because the answer is a bit subtle and it's important to understand. So convergence analysis for self-concordant functions. So this is just a different convergence analysis for Newton's method. So, by the way, if your interest is entirely practical, then none of this is of any interest to you in the following sense. We already know Newton's method A works well, unbelievably well in practice. That's point A. And point B, we know that we have a proof of convergence. It's true, the proof of convergence involves constants that you don't know and will not know. Number one. And number two, even if you did know those constants and plug them in, you'd get an upper bound on the number of steps that's ridiculously high and therefore useless. Now, if you're practically oriented, you say, I didn't care anyway. What I care about is that I can solve these problems with 100,000 variables in 15 steps very reliably, which generally speaking is true. It depends on the function, of course, but okay. So if you don't, if that's your interest, then the only thing you want to know about this is then this material is basically how would you prove, how would you actually get a real number that says that's the number of steps it takes to solve a linear program. Anyway, this is what you would use. Okay. So here's what it says. Everything depends on lambda. That's our old friend, the Newton decrement here. If it's bigger than a number eta, and eta, it actually you can even put in, I mean, you can get very deeply into this, and the eta would be, 0.09 something. You can get very deeply into this if you want to optimize the analysis. And it says the following. It says that the function value decreases by at least a number gamma if the Newton decrement is bigger than eta. Okay? And then it says once it's less than eta, it says twice the Newton decrement is less than twice the Newton decrement squared. Okay? Now, here's the most amazing, putting these two together, you get the following. It says that here's the number of Newton iterations. It says it's less than the initial function value minus the optimal value divided by gamma plus log 1 over epsilon. Okay, this we read as 5 or 6. I mean, I don't care, but that's 5 or 6. That's it. Okay. Now, here's the most amazing thing. These numbers here depend on alpha and beta. They're not hard to work out. If you use typical numbers of alpha and beta, and epsilon is 10 to the minus 10, seems like a quite reasonable final stopping criterion or something like that, then the numbers work out to 375 plus 6. It's 375 times the difference in the function plus 6. Now, by the way, with a lot of work, not much, well, with some work, you can actually analyze all this stuff and everything, instead of doing very sloppy bounds, you can actually come up with a number that's around 11, f of x0 minus p star plus, actually, and then the numbers, well, 6. 6 is our way of writing that. That's our special symbol for this.
Is this an upper or
An upper bound. That's an upper bound on the number of steps. Okay. All right, so you get this thing here. Now, here's the wild part. And this is like very cool right now because it basically says, look, here, there's several things are absent from this. If you look carefully here, you don't see n. You don't even see the dimension. You don't see n is gone, m is gone, l is gone. In fact, you can scan this sheet for a while, and it only depends on two things. That's alpha and beta. These are parameters. These are parameters in the line search. You know them because you choose them. So this is really one of those exceedingly rare things. This is a complexity analysis which actually passes the first step in actually being useful. I mean, beyond conceptually useful, right? In the sense that most complexity analysis looks like this. I walk up to you and I say, listen, if, and then I give you a long list of hypotheses. If this holds, then, and I give you a long list of conclusions. Now, usually the hypotheses are unverifiable, and the conclusions are uninteresting. But then when you point that out to the person telling you that, they say, oh, you've missed the whole point. You've totally missed it. This is for conceptual, it's conceptually useful. And then you go, oh, okay, thank you. And they go, can't you sleep better now that you know that if some things that are unverifiable were to happen, then some things that are uninteresting would happen? And you go, yes, thank you very much. No, I will sleep much better. Thank you. So, I mean, I'm not making fun of it. It's better than the opposite, where you just kind of code stuff up and run it. And so it is nice to know that if you're confronted by a gang of angry theorists in a back alley somewhere and there's no way out, that you can you can actually justify it. So that's good to know. Okay. So, but what's amazing here is that these are just numbers. It just says basically if you're minimizing log dead, or if you're minimizing this log barrier. Oh, pardon me. Sorry. Aren't you doing that right now? Yeah. So aren't you all happy now to know that in fact that is true? That for your codes, the number of Newton steps, I hope, in no case did it exceed this. There's a question?
You have a term in there for for the initial function value minus the optimal value, but isn't that totally dependent on your choice of coordinates?
No. No, that's a choice of you can multiply f. That's one thing. The choice of coordinates scales x inside. If you multiply by something x, that's a change of coordinates. If you multiply f, yes, it does. That changes everything. Okay. However, I'm allowed to scale f up. That just makes my bound worse. That's why I can't scale it down. That's why this is the case. Otherwise, I would say, really? It only depends on the difference between my starting and the final value? No problem. I'll multiply my function by 1e minus 10 and minimize that. Then this goes down to 1e minus 10, and it's 6 steps. But it doesn't work that way because you're not allowed to. You can scale it up. So good question, though. OK. So it's really quite beautiful, and it's good. I guess order is restored in the world because now your complexity analysis is at least aesthetically as elegant as the method itself. So that's good. OK. Yeah.
Does it depend on alpha and beta?
You can check. It's irrelevant how it depends on alpha and beta. It doesn't matter how this number changes.
It enters into gamma, right? Wouldn't it change how fast that thing grows? Or
yeah, it affects this. Yeah, so it does affect that. All right. So you can look at. You can actually try this out. Indeed, you can if you want. Now, in fact, what's going to happen since you're all running Newton methods now, today, yesterday, last night, I don't know, later this afternoon, you'll be running Newton methods. I don't think anyone here will find an instance where it takes more than, like, I don't know, 10 or 15 steps or something. Has anyone found any instance where it took more than that? Try any big ones? Actually, first of all, how many people have gotten their Newton thing up and running? Okay. Anyone, what's a typical number of steps? Okay. Anyone scale things up big? Anyone try like a several thousand variable problem or? What's that? Did you?
Ran out of memory while computing the Hessian and the inverse.
Ah, okay. Yeah, but you know how you can do that, right? You just make A sparse. Right? So everything would work. You make A sparse, I guarantee your code, exactly as it is, will go up to 100,000 variables. Just make it sparse. And don't make any mistake that promotes a sparse matrix into a full one. Because if it's 100,000 by 100,000, it'll just stop right there. It'll attempt to allocate memory and fail. So, okay. Okay. So it's an interesting thing. If you can play with it and all that. So what's cool about this is, first of all, just the fact that such a bound exists, because this is very, very unusual. Very unusual to have a bound like this. Now it's not that relevant. Even at 11, it's not that. Sorry. Even at 11, it's not such a great bound. Here's what's interesting. So here's an example. I think this is just log barrier. So this is exactly what you're doing. And here's ones where you actually just generate a random instance, solve it. By the way, after you solve it, you know P star. So you can plot P star and you can jot down the number of Newton steps required. I think these are various problems in various dimensions. It would look no different. Actually, it gets more favorable the larger the problem, but it doesn't matter. And you can see various things here. The bound, this bound wouldn't even fit on this. It would go from 6. It would go straight off, like right there. It's almost vertical, the bound here. Good news, all these points are, good news is all these points are below the bound. That's good. The interesting thing is, at least here, you can see something that looks like that. It looks like the constant in front here, actually, might be on the order of 1 or 2 or something like that. That's just empirical. No one can prove that. The best bound, with all sorts of work, you can whittle this 375 down to about 11. Probably if you worked harder, you could make it smaller. But the point is, it would appear that if you replace 375 with 2, you get a pretty good empirical estimate of a bound. By the way, what are these? What's that? Well, it's a problem with a pretty healthy f of x0 minus p star. So that's, which is to say, a pretty crappy starting point. But Newton's method got it pretty quick. So what is that? What do you call that?
Nearly quadratic.
Luck.
Luck. Yes, I think luck is the right answer. Right. So basically, I mean, remember, there are actually points way, way out there, way far away from optimum, where just as fate would have it, the Newton direction points you directly to the solution. Right? There are such points. I'm not saying there's a lot of them, but there are such points. So the point is, this is just luck. This is just, you started far away, and for some reason, the third Newton step just happened to be in a really, really good direction. Landed you made much better progress than you should have, and there you landed there. So these are luck. Actually, what's very interesting about this is it says that when we do complexity analysis, which we'll do like next week, it says actually you can give the same lecture, or you can talk and do analysis, and actually it's interesting, you can talk to 2 groups of people at the same time. You can talk to, like, your complexity theorist can sit on one side of the room, and then, but what we'll do is we'll define this to be C, a constant C. And on the left side of the room, we'll have the complexity theorist there. We'll say C is 375, and we'll have another one called D, and we'll say D is log 1 over epsilon. Okay? They'll sit over there, and we'll argue using C times F minus P0 plus D. Other people will sit on the right, and they'll say, look, I couldn't care less. I know it works. Obviously it works. I'm totally convinced. I've solved 1,000 convex optimization problems this quarter. None of that would have worked if this didn't work. I'm convinced. I'm not interested in the actual complexity. What I'm interested in is things like this. How should I choose the parameters to make this algorithm run fast? And I don't want some bound like 5,000 iterations. I want to know, how can I make it 22 as opposed to 66? That's the other extreme. They have no interest in that. You can talk to them because you say, oh, no problem, because we'll make this 1 and we'll make that 6. And they'll be satisfied too. Then we'll optimize the coefficients and things like that. You can then actually optimize algorithm parameters. We'll do this next week. We'll find out what the optimum are for the complexity theorists and for the people who are interested in the practical methods. And they'll be different. So, okay. All right. Let's talk about implementation, which is where linear algebra from last week comes in. So the main effort in each iteration of a Newton's method, it depends on, of course, evaluating the gradient and the Hessian and all that. But assuming in most cases, that's modest compared to actually solving. But that doesn't have to be the case. But in many cases, that's modest compared with solving for the Newton direction. You have to solve a positive definite linear equation. That's it, set of linear equations here. Okay. How do you do that? Simple answer is, if H has no structure or whatever, Cholesky. So you just do Cholesky here. So you do a Cholesky factorization, you do a backward, then a forward substitution, that's this, and so on. And then you can actually, as you're doing various calculations, for example, you get lambda is the norm of L inverse G. So you'll actually, when you actually do this, if you did a real implementation, you would actually find out that some of the things you're computing anyway are useful, like you'd get lambda here. And the cost is 1/3 n cubed flops. Now, if H has structure, then of course you can solve this much faster. For example, if H is toplets, if H is circulant, if H is banded, if it is banded arrow, any of these things you can exploit and solve this way, way faster. Okay, way faster than n cubed, which, by the way, already is not too slow. So to give an example where you would have a dense Newton system with structure, well, actually, I guess on the current homework, I think you're looking at a problem. It's quadratic, but in fact, solving that is one step of a Newton method. And that's an example. So you'd see the structure would come up in the linear algebra. The Hessian structure reflects sort of which variables couple nonlinearly to which others. And actually, after a while, you'll get used to looking at a problem and just saying, I know the structure. So if you'll look at signal processing, you can look at other problems, and you'll just know immediately what can be done. Another one is sparse. What does it mean if the Hessian is sparse, by the way, for a function? When is what would that mean? I have a function, and the Hessian is sparse. What does it mean? It has a meaning, very specific meaning. What does it mean? Exactly. Right. It's almost, it means that each variable couples nonlinearly only into a handful of others. That's roughly what it means. So it means, and by the way, if they decouple nonlinearly, it means they're separable. It means it adds up. So that's what it means. When would you get things like that? Well, that's kind of a vague question. But what would be some examples of cases where you'd have a sparse Hessian? How about if you saw something that looked like this? I'll just make it up here. Exp of, xi minus xi plus 2, I plus 1 there. Okay? There's a highly nonlinear function of a bunch of on Rn, right? That's highly nonlinear. Who knows why you'd ever want to use this? But let's imagine there it is. Okay? It's some weird thing where this is, I guess this is a smoothness measure or something. Who knows why? Okay? I guess it's bad. Xi can be a big above. This could be positive. That's bad. But otherwise, xi is, anyway, doesn't matter. I won't even attempt to make a practical problem where this comes up. But here's what I want to know more than anything. For this thing, what does the Hessian look like? Tridiagonal, exactly. So if you apply Newton's method to something like this, how fast is it going to be? How fast is it going to be? In n. N squared? 3n. It's n. It's going to be n. Okay? Because tridiagonal you can solve super fast. I mean, it's not. So if you were in something like this and you go, oh, no, I work on medical imaging. Our problems are really big. So you can take your Newton methods and shove them in put them in the garbage can as you come in. Because, other people in other fields, they work on smaller problems. We work on really big ones. Okay? A non-issue. You could 30 million variables, you could run full Newton's method, provided this is not medical imaging, this would be some signal processing type thing. But the point is, provided you understand, you recognize that the Hessian is tridiagonal here. Okay. All right. Here's an example of a dense one. This hopefully anybody would get, although you'd be shocked at how many people would not. Including especially large numbers of the people who would tell you all about the complexity theory of Newton's method. On and on. And many of them would have absolutely no idea that you could solve a problem involving this with Newton's method very, very fast. Nor would they have any idea how to do it, I might add. I'm saying that naturally because hopefully their students will watch this and then go tell their advisors. This is at other places. So, okay. All right, let's look at an example where you couple the material from last week with this one. Here's an example. This could easily come up. So here, you want to minimize a function that looks like this. It's a separable sum. So it's a sum of a bunch of scalar functions of the variables. This could be a regularization thing. I mean, who knows what this is? Some sick thing here, right? It might involve some, log likelihood, negative log likelihood function. I don't know. Then plus a nonlinear function of an affine function of the variable. So that's your function. How do you minimize that? Well, we'll assume here that this function is small. I mean that the size of this thing is small here. And in this case, if you take the Hessian of this, the Hessian of a separable function is diagonal. So this thing is, you get diagonal. By the way, that should light up all of you should have a section in your brain, or will, I hope, have a section in your brain devoted to equation solving complexity. It's sort of like, it'll be maybe near the visual cortex or something. It should light up big time when you see a separable function, because separable function should mean for you diagonal Hessian, and diagonal should be right at the top of the list on structures that should be exploited, obviously. By the way, anybody can do diagonal, so that's easy enough, right? If someone said, how would you minimize that? In fact, someone answer me. How would you minimize this? The sum of functions, you minimize each one separately, right? So, interestingly, what would be the computational complexity of that, just roughly? Order n? Right, okay. So, interesting thing is, just from a linear algebra, you know that too. Anyway, okay. Now, this makes it interesting, because now the Hessian has this form. It's diagonal plus A transpose H0A. H0 is the size of the height of A. So, for example, if this is 10,000 variables, and that's 1,000 here, let's say, or 100, let's make it 100. If that's 100 and that's 10,000, that's diagonal plus rank 100. It's 10,000 diagonal plus rank 100. This should be lighting up that center in your brain devoted to smart linear algebra, to being able to solve that. That should just set off everything. That's diagonal plus low rank or something like that. How do you actually solve this? It's pretty straightforward. You would factor H0, do a Cholesky factorization on H. That's the small one. So if this is 100 by 100, that goes down in microseconds, right? Maybe a millisecond, something like that. But I mean, fast. You do this. Then you write this. This is just the elimination, but done with Cholesky factors. You write it as d delta x plus this, where you introduce a new variable. The new variable is going to be wherever it is, H0A. So you write it this way. You factor this. You can solve these things. You can eliminate delta x from the first one and so on. And you end up forming this matrix. But the point is, that's the small dimension. That's 100 by 100. Okay. Now, you probably haven't done enough of these to know immediately what the computational complexity is. But it turns out actually solving this 100 by 100 system is 0. The dominant actually cost is doing this multiplication right here. That's what actually dominates. It's a matrix multiply. So it's 2 p squared n. But in particular, if this was like size 100 and that was 10,000, this would go down like really, really fast. Okay? And it's interesting. This is a great case to contrast with if you go back and, I don't know, imagine like the Apollo 1 or something like that. Go way back and imagine, whole books and things like that attempting to avoid Newton's system because, a Newton system with 50 by 50 was like a big deal. And you just did it for a 10,000 by 10,000 dense system. Now, you never formed the matrix H here, ever. If you did, it would be all over. Just forming that matrix would, first of all, you couldn't store it. 10,000 by 10,000 you could. But make it 100,000 by 100,000. Now you can't store it. Take you too long to compute it and all that. So this is a perfect example where there's not that many people, by the way, who would know this, even though what we're talking about now is just putting together like 6 or 7 things, each of which is not particularly complicated. You can solve this problem really, really effectively if you know what you're doing. That's this one here. So, okay, so that's just one example. There's tons and tons and tons of others. Okay, so that finishes up our tour of Newton's method.
How would you determine the function decomposition with the psi i's? Would those be given to you?
Oh, these are given to you. Yeah, this is just some weird. These functions are given to you.
Oh, so something you figure out from looking at your.
Oh yeah. By the way,
your data.
It depends. You have to know f has this form.
Okay.
If someone says, no, please write a Newton method, but the only thing I'm going to give you is the following. I'm going to give you a pointer to a function that will return the value, the gradient, and the Hessian of f. If someone does that, you're screwed. You can't, this won't scale to more than 1,000. Okay? And it'll be super slow. Right? So the point is, if someone gave you this matrix, that's end of story. It's all over. Once they've given you this matrix written this way, you can't do anything. Nothing you can do. The key is to know that it has this form. And so you have to be, so if someone else is creating these matrices, they have to pass you a data structure that gives you D, A, and H, 0.
And B also, right? Lowercase b.
No, just to calculate H, that's all you need to know.
Oh, okay.
But that's all you need to know. So, okay. Any more questions about this?
I've got a quick question.
Yeah.
On the self-concordant down, there's the absolute value of the third derivative less than constant second derivative.
Yeah.
What if the second derivative were negative?
Okay. I got asked that question by someone very famous once. So, okay. The functions are convex.
Okay.
Right. So self-concordance, that's a very good point. Self-concordance only applies to convex. Or actually, it's interesting. If you look back at the inequality, you'll realize a function could only be, if it's self-concordant, that subsumes convexity. Let's see if I can find that inequality. I'll find it somewhere. Oh, here it is. Okay. Yeah. So one way to say it, well, no, I'm sorry. Okay, here. So, all right. The right way to look at this is the following. I guess we should say, I guess to make this precise, we'd say convex here, there. That's a good point. So what you would say is something like this. The 3/2 power doesn't make any sense at all if it's negative. I mean, unless you're in a complex analysis class, right? So the 3/2 power, for this even to make sense, this part right here, you have to have f prime prime positive. Non-negative, which means it's convex. So. Okay. Yeah.
Compose certain matrix into the sum of structured matrix and the low rank matrix?
So that's a great question. So the question is, can you detect structured plus low rank or something? It's actually a huge field. There's a lot written on it. And let me tell you what I know about it, which is a strict subset of what is known about it. And I'll tell you this, there are some obvious cases where you should be able to do it. For example, you can detect if a matrix is a multiple of the identity plus a low rank matrix, because that you would do by eigenvalue decomposition. Okay, so that one you can actually detect. And although it's true that eigen decomposition would cost you n cubed, right, which would kind of ruin the whole thing. I mean, unless you're going to use that low rank structure and you're going to amortize it across many, many uses. There's actually ways to detect if a matrix is a multiple identity plus low rank. Diagonal plus the low rank is actually a famous kind of a semi-open problem. I know that there's a lot known about it, some not, and things like that. It comes up in statistics, actually. It's a big deal. I forget what it is. It corresponds to determining factors where you don't know. It's a factor model, and you don't know the individual variances. So that would be it. So for example, to write this, right, where that's a covariance matrix, this has a very simple interpretation. It basically says that there are factors underlying the vector observations you're seeing, a small number of factors. For example, let's do this in finance. That'd be a perfect example. Okay? In fact, that's where models of this are extremely common. So, one factor would be the whole market. Another factor would be some sector or something like that. But the factors, there might be like 5 of them. The diagonal here are sort of, if this is like a returns covariance matrix, the diagonals are interpreted as the firm-specific variances, and they're independent. So there'd be a lot of interest in writing models like this. I guess someone in the class actually pointed out the following. If this is rank 1, you can actually determine if a matrix has diagonal plus rank 1 structure. That you can check. But in general, like the low rank structure, you can't check with a diagonal here. For other things, there's, it's even more complicated, like how would you, but I actually think since you asked, I'll actually say a little bit about it. I think it's something like I think the situation here is like disciplined convex programming, right? So when you first do convex optimization, what you want to do is write a modeling language where you can write down anything you want, and then some program will analyze it, come back, and say, "Oh, it's your lucky day. It's convex." I mean, that's kind of the most natural thing. You write what you want to do, go to lunch maybe because it might take a long time, and then it comes back and says, "Hey, you're in luck. You wrote a convex problem." You think about that, you can actually implement things like that. They actually do kind of work and stuff like that, but it's completely the wrong way to do it. Because when you do that, when you're typing in your problem, it's like a monkey at a typewriter typing in something, hoping it's convex. If it's convex, you don't know why. You don't know which signs in your problem you can change with no effect whatsoever, and others will completely screw it up. You know what I'm saying? So it's better to do disciplined convex programming like you've been doing, I think, because it means you know what you're doing. So actually, I think maybe someone should make something that's disciplined linear algebra, where the goal is not to discover some structure that you or one of your fellow workers, fellow researchers or whatever, obscured by multiplying this out. This doesn't apply to raw data, by the way, of course. Obviously there, it's not that somebody obscured the sample returns. This is a model. But in the case of working with stuff, you would actually want something called, like disciplined linear algebra, where you'd have an interesting data structure. You'd store things as diagonal plus low rank, and that would actually be tracked and taken care of. So that's, I think, what you'd really want, to tell you the truth, is something that works that way, not something that kind of discovers structure. The same way with convex programming. I think it's better to be given a set of atoms, a set of rules that come straight from the math. And you just follow those, everything's cool. So that's my thoughts on it. But okay. So we'll turn to, was there any other questions about this? Okay, we'll turn to equality constrained minimization. So this is, it's going to turn out to be not much different from the unconstrained case. So we want to minimize f of x subject to ax equals b. We'll assume A is fat and it's full rank. I mean, in particular, ax equals b is solvable. And we'll also assume that the problem is bounded below, and f is convex and continuously is twice differentiable as a continuous second derivative. Now, the optimality conditions here are simple. It's if and only if there exists a nu such that the gradient plus A transpose nu equals 0. So that's the classic Lagrange multiplier rule. However, in this case, it's if and only if, right? There's no constraint qualifications of any kind here. Just no, don't even have to apologize. These are the necessary conditions. So another way to think of it is this, is you really want to solve a set of n plus p equations in the variables x star and nu star, which just coincidentally happen to have dimension n plus p, right? Because this is n equations, and that's p equations. So you can say that the same way when you do unconstrained minimization of f, you can say, well, look, my job is really to solve the n nonlinear equations in n variables. Nonlinear, by the way, unless f is quadratic, in which case this is linear. But in general, nonlinear equations, that's what you're doing. N equations, n unknowns. That's what Newton's method is really doing, for example. Here, it's not much different. In fact, you want to solve n plus p equations in n plus p unknowns. But there's actually some structure here. Like, for example, the added p equations are linear. These are the nonlinear ones. And indeed, they are linear in the nu. So it's not a completely general set of nonlinear equations. Okay, let's look at some, the most important case is quadratic. So if you minimize a quadratic subject to an equality constraint, this is a positive semi-definite. We'll get to that, though, in a minute. Then you write this out, and you just say the gradient. You just write out these conditions. I mean, the gradient here is, did I put a half in? Yeah, I did. Okay, so the gradient is px plus A transpose nu. It's a set of linear equations, which you write this way. The top, by the way, these have names. The bottom part is actually primal feasibility. That's exactly what it is. That's what this bottom part is. It's stupid. It says A x star equals B. Well, fine. Okay? The top one is actually dual feasibility. So the top one is dual, because to say this says that nu is dual feasible here. That's exactly what this means. So that's dual feasibility. So this is the anyway, we'll just leave it. This is the condition. By the way, some people call, if you take p x star plus a transpose nu here, and say plus q, or this thing, I should say this. So some people refer to this thing as the dual residual, and they would call that RD, and they would call AX minus B, or B minus AX, it wouldn't matter, they would call that the primal residual RP. And so the optimality conditions is that RP and RD should both be 0, the residuals. Okay, so back to the quadratic case. When you write this out, you get a set of linear equations like this. Now, that's not a big deal. The solution is this matrix inverse times that. Now, this matrix has a name. It's called the KKT matrix associated. This is the Karush-Kuhn-Tucker condition, is what this is. Very famous, actually. In fact, people just call this KKT matrix. So it comes up in lots of fields. By the way, it doesn't just come up in optimization. It comes up in like mechanics and all sorts of other areas. This comes up. And it's an interesting matrix. It looks like this. Its bottom is a 0 here. It's got an A and an A transpose here. And it's got a positive, we'll assume positive semi-definite, positive definite 1-1 block. So that's a so-called KKT matrix. And it's non-singular if and only if the following is true. On the null space of A, P is positive definite. That's the condition here. So that's exactly the condition. And that's the same, completely equivalent to P plus A transpose A is positive definite. Period. And this makes perfect sense. It says that here, A transpose A is positive definite, of course. This thing can have a null, the null space of this is exactly the null space of A. So what you need is you need P to step in and be positive on the null space of A. I mean, I'm just reading this equation for you. That's what this is. That's why these are equivalent. Okay, so this is the so-called KKT system for minimizing a convex quadratic with equality constraints. It's a set of linear equations. By the way, it's linear equations already with structure. It's got block structure. It's got this weird 2x2 block structure. Okay. Now, you can eliminate equality constraints. That's straightforward, and it's sometimes the right thing to do. That works like this. You write the solution set of a set of linear equalities. This is in so-called constraint form. People call that constraint form because it's the set of x that satisfies some equations. You can also write it in so-called free parameter form. If you write it in free parameter form, you write it this way. It's x hat, or sometimes xp. Well, p collides with that one, but anyway, it means particular. It's a particular solution of ax equals b plus an element of the null space. I mean, obviously this is the case, right? Set of x such that ax equals b is equal to x particular plus the null space of a, period. Okay? So that's the condition. So, okay. Now, here, to write this out more explicitly, you just calculate a matrix F whose columns span the null space of A. And then this would give you this free parameter representation. Now what you do is no problem. You change variables, and your equality constraint problem becomes this unconstrained problem, because now you have a free parameter representation of any x that satisfies ax equals b. That's this thing. Okay? And you can work out various things. It turns out if you really wanted to solve this, if you had to write a code, for example, that solves this or something like that, and or that solves, the original problem here, that solves this thing, and someone tells you, no, your code must return nu star as well as x star. And you say, why? And they say, because we don't trust you. Because whoever calls this is super highly critical, and whoever calls you is going to add something that checks the primal and dual residuals. Dual and primal residuals, just to check you. So you must return a certificate. And just that's the way we do things here. If internally you solve it by elimination, you can actually still return the certificate, because the certificate is just this. You can work that out. That's exactly what, you can check that in fact these things work. So although you solve it by elimination, you can actually return the certificate. So let's look at an example here. optimal allocation with resource constraint looks like this. So you minimize a sum. So basically I have a set of resources. That's our total amount of resource. That's B. And I have to divide that up among n users of the resource. I guess these can be negative as well, but I don't really care. And I want to minimize some cost of this thing. But the costs are separate. They're separate. So I want to minimize f of x1, f1 of x1 plus x2. And each person has a different cost function and so on. Some care about getting a lot, some care less or whatever. And I want an allocation that sort of minimizes the total irritation or cost across the population while respecting my resource constraint. So that's this problem here. Okay. Well, what you could do is, it's very, very simple. What you do is this. Imagine x1 through xn minus 1 as free variables. Once you've fixed these, then xn is simply b minus x1 like that. And by the way, this is the same as choosing f to be this matrix here. And x hat is b times en here. That's all. That's the particular solution. The particular solution is give all the resources to the nth user. That's the particular solution. It is a solution. I mean, sorry, it's a feasible point. The reduced problem looks like this, which we could then minimize now. By the way, when you see this, and if I asked you, just going back to what we were just talking about just not very long ago, if I asked you to use Newton's method to minimize this, what would you say? Does it look familiar? Tell me about the Hessian of this chunk, diagonal. Can you tell me about the Hessian of that? I know what it is. You might not be able to do it in your head. What is it?
Rank 1.
It's rank 1. It's an outer product. So it says that if you wanted to solve this problem by Newton's method, if you didn't know what you were doing, that would be the most common case. Not, of course, for you, but for people who haven't taken this class, or an equivalent one. You would say, well, that's n cubed, because you'd form this thing. But you now know that this resource allocation problem can be solved in order n, because it's going to take 15 Newton steps, like max, and each Newton step can be solved in order n. Why? Because the Hessian, though dense, is diagonal plus rank 1. I think I'm repeating myself. I'm repeating myself, right? But that's okay, because these are really important things. So that means actually you can do this resource allocation with a million users. It's absolutely no problem. You can do it in MATLAB if you know what you're doing. So, okay. Okay, so this is elimination. Okay, so how, there's another method. Well, it turns out it's only nominally another method because it turns out to be equivalent. And that's to directly extend the idea of Newton's method to problems with equality constraints. That looks like this. What you do is you look at the Newton step, and there's lots of ways to explain what it is. It's an extension of it. But anyway, you write down the KKT conditions where you put in the local, the Hessian. So you write down that's the KKT matrix. That's a step in your x, and W is a dual variable. And you write this. Now, this, by the way, if there were no, let's see, there we go. Can I do it? Almost. I did it. There we go. So you can see that without equality constraints, it reduces to the Newton step, because it's simply the Hessian times the gradient. Hessian times the Newton step is equal to negative gradient. That's Newton. So it reduces to that. And here are some interpretations. So one is this. It's completely natural. It says I'm solving this problem, minimize f of x subject to ax equals b. And it goes like this. The first thing you do is this, is you have a current x, which is a guess, and it's feasible. So it satisfies ax equals b. And I want to know, what should I do? Well, what I'll do is I'll develop f into a second order Taylor series at my current point. And I will get this thing. Okay? Now that right there is a quadratic function of v. I'm thinking of a tentative step, v. Okay? So I would get this. And instead of minimizing f, which I don't know, I'll minimize my quadratic model, but subject to ax equals b. Well, ax equals b, so av has to be 0. So v has to be in the null space. That makes perfect sense. If you are at a point which is a solution of ax equals b, and someone is asking, and you're considering directions to go in where you will still satisfy ax equals b, you have to move in the null space. There's nothing else you can do. Therefore, if you work out what this is, it will say AV equals 0. Okay, you must move in the null space. And the second one up here, this will be a quadratic. And if you actually work out the conditions for that quadratic, it's exactly this. Note that the second term here says A delta x equals 0. It says that you will only look at, it will always generate a direction which is in the null space, which means it won't mess up your equality constraints. If they're already satisfied, they will remain satisfied, actually independent of the step length you take, because you're moving in the null space. Okay. Another way to do it, to interpret the Newton step, is this: is you say, is you take, is you look at the optimality conditions, which is this here, and you say, look, I'm going to take a tentative step, which looks like this. That's my tentative step. In fact, if I could find v that satisfied this, I'd be done, because then x plus v would be optimal. The problem is that this thing here is nonlinear. So what I'll do is I'll have an affine approximation of this. And I'm going to call that the gradient at x plus then the Hessian at x times v. I will replace this expression with that. If I plug this in here to these, I get the Newton step again. Okay? Now, so that's the Newton step for equality constraints. Now, in this case, there's a Newton decrement as well. And there's many formulas for the Newton decrement. And I have to warn you, many, but not all of them, actually are that are valid in the case of unconstrained. Some of them are invalid in the case of the constrained. So correct formulas are these. That's one. That's another one. Another one. Another thing it has the exact same interpretation. Lambda, 1/2 lambda squared, is your predicted decrease in f. By the way, this tells you that if lambda is small, then your decrease in f is going to be small. It predicts a small decrease. However, this formula is wrong in this case. It's just wrong. It's just not right. So you have to watch out with these. And then let me just say what Newton's method is for equality constraints. It's very, very simple. You start with a point that satisfies ax equals b, and it's in the domain of f. And you compute the Newton step and the backtracking and the Newton decrement. You quit if the Newton decrement is small enough. Otherwise, you do a line search. Backtracking is fine. And then you update. It's a feasible descent method. It's affine invariant. So you can change coordinates. Makes absolutely no difference. You get a commutative diagram. In particular, scaling has a second order effect on the method. And in fact, if it's all done in infinite precision arithmetic, which it never would be, but imagining that it were, it would have no effect whatsoever on the method, scaling. Okay, so it turns out we don't need to do any theory for this, because it turns out that Newton's method this way is identical to Newton's method with elimination. You get exactly the same iterates. Therefore, everything we know, self-concordance, classical analysis, practical performance, such as, for example, you've found out a little bit about so far, it's all the same. But you might protest and you might say, now, wait a minute. When you do elimination, there's lots of choices for f. F is any matrix whose columns span the null space, or are a basis for the null space of A. So there's lots of ways to do elimination. Surely all those methods can't give you the same iterates. The answer is they do. Of course they do, in Newton's method, because that amounts to a change of coordinates, and it's completely insensitive to that. So they all give exactly the same. Okay. So this is so you don't need any separate analysis or anything and anything like that. So that's Newton's method, and you will get to apply Newton's method with equality constraints on your last homework. So it's not, but it's not that hard. By the way, I'm curious how many people, just for fun, how many people actually poked around on the web to look for source code? I mean, there's no dishonor in it. You should do this. Did everyone just write for their current homework, did they write it from scratch? It's fine. I told you last time, it's not like it's a secret or anything. 3 clicks and you can go to Google, you type the right phrase. Not even the right phrase. You could just, and you'll find source for it. But I think you should do that only if you get stuck, or if you want to look at our implementation. It's all on the web. You could, because all the source code for the entire book is on the web. So you can find our code, and you can see which you like better, yours or ours, or something like that. So I mention this only if you get stuck. There's no point banging your head or something like that on these things. Anyway, so same for this stuff. Okay. Now, I want to mention something about Newton method for infeasible points. It's a very interesting method, and it works like this. It says, suppose, and by the way, this is now so-called. It's going to lead to an infeasible method. You actually have the idea of a Newton step, even when you are not in the feasible set. That's weird. And let me even just draw a picture, and I guess we'll cover this next time, but let me just draw a picture of that. Here's your equality constraints. And let's say your function looks like this. Here's some level sets of your function or something like that, okay? So that's the optimal point, right? Yeah, okay, that's fine. So here's some level sets. Now, if you're here, the Newton direction, I should have drawn it more skewed so the center was over there. But I didn't, sorry. So the Newton direction is probably going to want to point like that, unconstrained. But you can't, because you have to stay, well, you have to have something in the null space, and you have to be feasible, so it's going to point you in that direction. Okay? What's really odd is the following. You can actually imagine that you're here. Now, when you're here, you got serious problems, because for one thing, you're not feasible. The constraints are AX equals B. You don't have AX equals B here because you're off this thing. Your second problem is that you're not optimal here, right? So you can actually define a Newton step off here, and it's going to actually combine two things. One is an urge to kind of return. I'm anthropomorphizing it, but that's okay. An urge to return to feasibility, or to approach feasibility. That's number one. And number two, simultaneously to decrease f. Okay? And by the way, if you're here, you could actually easily be in a situation where the urge to return to feasibility will overwhelm, and you'll actually have an increase in f. That would be clear. For example, suppose I was at the unconstrained minimum here. Okay? Well, there's actually norm grad f or whatever is 0. There's no direction you can go in and make f smaller. That's obvious, right? If you're here. However, you're not feasible. So in this case, you're going to point towards this line here. And that, of course, will mean it's going to be an ascent direction in f. But you have to, because you're not feasible. So although you have a mighty fine function value there, it's not feasible. So, okay. So you have this idea of the Newton step when you're off here. By the way, the Newton step will be such that if you took a full step, it'll actually get you back to the line exactly here. That Newton step is described this way. And you put here, this is in fact R primal. That's the primal residual. Note that once you're feasible, if x were feasible, this would be 0. And this would revert to the standard Newton direction. But if you're not feasible, this second part down here, which is a 0 when you're feasible, actually contributes to your direction, and it's a direction that points you towards feasibility. In fact, it points you to a point where if you took a step of 1, you would be feasible. So, okay, I think we'll continue this from here next time.